focus area of second chapter plus 1, chapter 2, structure of atom. Structure of atom. Okay. First question, Rutherfords atom model. Rutherfords atom model, or it is otherwise called Rutherfords planetary model. Okay, Rutherfords planetary model. First point, entire mass and charge. Entire mass and charge of an atom. Charge of an atom is at its center. At its center, called nucleus. Called nucleus. Called nucleus. The entire mass and charge of an atom is at its center. That center is called nucleus. That center is called nucleus. Mass and charge of an atom is concentrated at this center. This center is called nucleus. Okay, first point. Then second point, nucleus is surrounded by negatively charged electrons with very high speed. Okay, nucleus is surrounded by negatively charged electrons. Negatively charged electrons with very high speed. With very high speed. Okay. Electrons are revolving around the nucleus with very high speed, and that electrons have negative charge. Nucleus is surrounded by negatively charged electrons with very high speed. Then third point, there is an electrostatic force of attraction. Electrostatic force of attraction is in between nucleus and electrons. Nucleus and electrons. Nucleus is positively charged and electrons have negative charge. Then there is an electrostatic force of attraction between these two charges, or nucleus and electrons. Okay, there is an electrostatic force of attraction is present in between nucleus and electrons. And last point, most of the space in an atom is empty. Most of the space in an atom is empty. Okay, 99% of an atom is empty. Okay, these are the points of Rutherford's nuclear model of atom, or Rutherford's atom model, or Rutherford's planetary model of atom. This is the first question in our focus area, Rutherford's atom model. Okay. Second question, demerits of Rutherford's atom model. Demerits. What are the demerits? Demerits of Rutherford's atom model. Rutherford's atom model. Demerits of Rutherford atom model. First one, cannot explain stability of atom. Cannot explain stability of atom. Stability of atom. Second point, cannot explain line spectrum. Cannot explain line spectrum. These are the two demerits of this Rutherford's atom model. Rutherford's atom model cannot explain stability of atom, and also Rutherford's atom model cannot explain line spectrum. Then third question, quantum theory. Quantum theory. Quantum theory. Okay. Quantum theory was introduced by Max Planck. It was introduced by Max Planck. Okay. First point, energy is emitted or absorbed. Energy is emitted, emitted or absorbed in the form of small packets packets called quanta or photon, called quanta or photon, quanta or photon. This is the first point. Energy is emitted or absorbed in the form of small packets called quanta or photon. This energy is radiant energy which is emitted not continuously but discontinuously in the form of small packets of energy. Each energy packets are called quanta or photon. That we can write, energy is emitted or absorbed in the form of small packets and each packets are called quanta or photon. Second point, energy of radiation directly proportional to frequency nu, okay, or energy equal to a constant h into nu. This constant h is called Planck's constant. Planck's constant. Planck's constant. Value of h equal to 6.626 into 10 raised to minus 34 joule second. Joule second. Okay. Then third point. Third point. Energy is always an integral multiple of h nu. That is C equal to nh nu, where n equal to 1, 2, 3, 4, etc. Energy for first state, instead of this n, we have to write 1, that is 1 h nu. Energy of second state, E2 equal to 2 h nu. Energy of third state, E3 equal to 3 h nu. Then energy difference, E2 minus E1, 2 h nu minus 1 h nu, that is equal to h nu. E3 minus E2, 3 h nu minus 2 h nu, that is equal to h nu. That is, energy is always an integral multiple of h nu. This is quantum theory, which was introduced by Max Planck. Okay. Then fourth question, photoelectric effect. Photoelectric effect. Photoelectric effect. This phenomenon was introduced by Hertz. Okay. When light having suitable frequency falls on metal surface, electrons are ejected. This effect is called photoelectric effect. This effect is called photoelectric effect. Photoelectric effect. When light with suitable frequency falls on some metal surface, consider this is a metal surface. When light with a suitable frequency falls on it, electrons are emitting from this metal surface. Electrons are emitted. This effect is called photoelectric effect. These emitted electrons are called photoelectrons. Emitted or ejected electrons are called photoelectrons. Electrons are called photoelectrons. Emitted or ejected electrons are called photoelectrons. This is photoelectric effect. It was introduced by Hertz. Next question. What are the features of photoelectric effect? First one. Electrons emitted during photoelectric effect during photoelectric effect photoelectric effect are called are called photoelectrons are called photoelectrons. Okay, that is the first feature. Electrons emitted during photoelectric effect are called photoelectrons. Okay. Second feature, energy of photoelectron depends upon frequency of light. Depends upon frequency of light. Energy of photoelectron depends upon frequency of light. Third point, number of photoelectron. Number of photoelectron depends upon number of photoelectrons depends upon intensity of light. Depends upon intensity of light. Intensity of light. Then fourth point, minimum frequency required for photoelectric effect is called threshold frequency. Minimum frequency required for photoelectric effect. Photoelectric effect is called threshold frequency. Threshold frequency. Minimum frequency required for photoelectric effect is called threshold frequency. Okay. Then sixth question. What is Einstein's explanation of photoelectric effect? Einstein's explanation of photoelectric effect. Einstein's explanation of photoelectric effect. Einstein's explanation of photoelectric effect. Okay. When light with high energy falls on metal surface, when light with high amount of energy falls on metal surface, energy of that light is used for photoelectric effect. Some part of energy is used for photoelectric effect. Energy for energy for photoelectric effect. Photoelectric effect. And remaining part of that energy is used as kinetic energy of electron. Okay, when energy of light is very high, some part of this energy is used for photoelectric effect and remaining part of energy is used for kinetic energy of photoelectron. Kinetic energy of photoelectron. Energy of light can be represented as h nu equal to energy for photoelectric effect can be represented as h nu 0 plus kinetic energy can be represented as half mv square. H Planck's constant, nu frequency of light, h here also Planck's constant, nu 0 threshold frequency, m mass of electron, v velocity of electron. H nu, this h nu 0 on left hand side becomes minus h nu 0 equal to half m v square. Here h is common, so h into nu minus nu 0 equal to half mv square. This is Einstein's explanation on photoelectric effect. Once more, when energy of light is very high, some part of energy is used for photoelectric effect and remaining part is used as kinetic energy of photoelectrons. Therefore, h nu equal to h nu 0 plus half mv square, h nu minus this h nu 0 equal to half mv square, h into nu minus nu 0 which is equal to half mv square, where h is Planck's constant, h Planck's constant, h Planck's constant, nu frequency of light, nu 0 threshold frequency, threshold frequency, M. Mass of electron. M. Mass of electron. V. Velocity. Velocity of photoelectron. That is Einstein's explanation of photoelectric effect. H into nu minus nu zero equal to half mv square. Okay. Our next question. Line spectrum of hydrogen atom. Okay. Line spectrum of hydrogen atom. Line spectrum of hydrogen atom. Spectrum produced by hydrogen atom is called hydrogen spectrum. Spectrum produced by hydrogen atom is called hydrogen spectrum. Is called hydrogen spectrum. Okay. This spectrum contains large number of lines, number of lines of definite frequency, So, hydrogen spectrum is called line spectrum. So, hydrogen spectrum is called line spectrum. These lines are included in 5 series. These lines are included in 5 series. They are: first one, Lyman series. Second series, Balmer series. Third series, Passion series. Fourth series, Bracket series. And fifth series, Fund series. There are 5 series. Okay, here N1 is equal to 1. Here 2. Here 3. Here 4. Here 5. In Lyman series, N2 equal to 2, 3, 4, etc. Here 3, 4, 5, etc. In Passion series, 4, 5, 6, etc. Value of N2. In Bracket series, 5, 6, 7, etc. And in Fund series, value of N2 equal to 6, 7, 8, etc. Okay, Lyman series, it is present in ultraviolet region. Balmer series is present in visible region. The only series which is present in visible region is Balmer. Passion, Bracket and Fund series are present in infrared region. Okay, the wave number of each lines in hydrogen spectrum, nu bar, equal to 1 by lambda, equal to RH into 1 by N1 square minus 1 by N2 square. Okay, this equation is called Rydberg equation. It is used for finding out wave number nu bar. From this equation, we can also find out lambda wavelength. Here, nu bar, wave number, nu bar. Lambda is wave length. N1 and N2 are these values, 1, 2, 3, 4, etc. values. And RH is called Rydberg constant. This RH is called Rydberg constant. RH equal to 10, 96, 77 centimeter raised to minus 1. RH equal to 109677 centimeter raised to minus 1. That's all about line spectrum of hydrogen atom. Line spectrum of hydrogen atom. Next question, Bohr atom model. Okay, Bohr atom model. Bohr atom model. Bohr atom model. Okay, here first point. First point, electrons are revolving. Electrons are revolving around the nucleus. Around the nucleus in certain fixed paths. Certain fixed paths called orbits or shells. Orbits or shells. They are K, L, M, N, etc. Negatively charged electrons are revolving around the nucleus with very high speed in certain fixed paths, and the paths are called orbits or shells. These paths are K, L, M, N, etc. Okay. Second point, when electrons are in a particular orbit, there is no loss or gain of energy. When electrons are in a particular orbit, there is no loss or gain of energy. So, orbits are called energy levels. Orbits are called energy levels. Called energy levels. Why? Because when electrons are in a particular orbit, there is no loss or gain of energy. Third point, when electrons are revolving around the nucleus in circular paths, there should be angular momentum. There should be angular momentum. That angular momentum, angular momentum, angular momentum of electron mvr, mvr is always an integral multiple of h by 2 pi. That is mvr equal to nh by 2 pi. M mass, v velocity, r radius of orbit, n number, h Planck's constant. Angular momentum mvr is always an integral multiple of h by 2 pi. And fourth point, energy difference between orbitals delta E. Energy difference between orbitals delta E equal to E2, second state minus first state, here equal to h nu. Energy difference between orbitals, successive orbitals E2 minus E1 equal to h nu. These are the points of Bohr atom model. This is Bohr atom model. Electrons are revolving around the nucleus in certain fixed paths called orbits or shells. They are K, L, M, N. Orbits are called energy levels because when electrons are in a particular orbit, there is no loss or gain of energy. Angular momentum of electron mvr is always an integral multiple of h by 2 pi. Energy difference delta E equal to E2 minus E1 equal to h nu. Next question, merits of Bohr atom model. Merits of Bohr atom model. Merits of Bohr atom model. Atom model. First merit, it explains stability of atom. It explains stability of atom. Second merit, it explains line spectrum. It explains line spectrum. First one, it explains stability of atom. Second one, it explains line spectrum. Third point, this Bohr atom model is used for finding out radius of orbit Rn equal to n square a0 by z, where n is the number of orbit. A0 is called Bohr radius and its value is 52.9 picometer. Z is atomic number. Z is atomic number. Okay, it is used for calculating radius of orbit Rn equal to n square a0 by z. N is number of orbit, a0 is Bohr radius and its value is 52.9 picometer, z is atomic number. Fourth point, it is used for finding out energy of electron. Energy of electron, En equal to minus Rh into Z square by N square. Okay. Energy of orbit, energy of first orbit or second orbit or third orbit, etc. Energy of electron in that orbit. En equal to minus Rh into Z square by N square, where Rh is Rydberg constant. Rh is Rydberg constant. Z is atomic number. N is number of orbit. Okay. Next question. Demerits of Bohr atom model. Demerits. What are the demerits of Bohr atom model? Demerits of Bohr atom model. Demerits of Bohr atom model. Demerits of Bohr atom model. First point. Cannot explain. Cannot explain. Fine spectrum. Bohr atom model cannot explain fine structure of line spectrum or fine spectrum. Second, cannot explain Stark effect. Cannot explain Stark effect. Stark effect means splitting of spectrum in electric field. Electric field. Splitting of spectrum in electric field. That is called Stark effect. Bohr atom model cannot explain Stark effect. Third point, Bohr atom model cannot explain Zeeman effect. Cannot explain Zeeman effect. Zeeman effect means splitting a spectrum in magnetic field. Splitting a spectrum in magnetic field. Fourth point, cannot explain spectrum of multi-electron atoms. Cannot explain spectrum of multi-electron atoms. Multi-electron atoms. Atoms which contain more than one electrons. They are called multi-electron atoms. Spectrum produced by multi-electron atoms cannot be explained by this Bohr atom model. These are the demerits of Bohr atom model. Okay. Next question. Dual character of matter. Dual character of matter. Matter show two characters. They are first one particle character. Particle character. Particle character. Second one wave character. Wave character. These are the dual character of matter, particle character and wave character. Next question, de Broglie's equation or de Broglie's relation. De Broglie's equation or de Broglie's relation. This equation is used for finding out wavelength of matter waves. Wavelength of matter waves, lambda equal to h by mv or lambda equal to h by p, where lambda is wavelength, h is Planck's constant, m mass, v velocity. Instead of this m into v, we have to write p. Therefore, equation becomes lambda equal to h by p, where p is the momentum. P is the momentum. Next question. Uncertainty principle. Uncertainty principle. Principle. This principle was introduced by Heisenberg. This principle was introduced by Heisenberg. It is impossible to determine simultaneously both position and momentum. Position and momentum of moving microscopic particle. microscopic particle accurately. This is uncertainty principle. It is impossible to determine simultaneously both position and momentum of a moving microscopic particle like electron accurately. Okay, it is not possible to determine simultaneously both position and momentum of a moving microscopic particle. That particle is seen only through microscope. Microscopic particle, very small particle, it is seen only through microscope. It is not seen through naked eye. Okay, particle accurately. If we get the position clearly, then there should be an uncertainty in its momentum or change in its momentum. If we get the momentum clearly, then there should be an uncertainty or change in its position. Okay, mathematical expression of the principle can be represented as mathematical expression of the principle can be represented as delta x into delta p greater than or equal to h by 4 pi. This is the mathematical expression of uncertainty principle, where delta x is uncertainty in position, that is delta x. Delta p is uncertainty in momentum, okay. Then delta x into, instead of this delta p, we have to write m delta v. Instead of this delta p, we have to write m delta v greater than or equal to h by 4 pi, where m is mass, and delta v is uncertainty in momentum. Uncertainty in velocity. Delta v is uncertainty in velocity. Okay, delta x into m delta v greater than or equal to h by 4 pi. M is mass and delta v is uncertainty in velocity. Significance of the principle is, it is applicable to microscopic particles. It is applicable to microscopic particles only. Applicable to microscopic particles. Okay, it is not applied to large objects just like bus, cricket ball, okay, earth, moon, etc. It is applicable only to microscopic particles. This principle is applicable to microscopic particles only. Next question, quantum numbers. Quantum numbers. Quantum numbers. Okay. A set of numbers used for explain the characters of orbitals and electrons in an atom. They are called quantum numbers. A set of numbers used for explaining the characters of orbitals and electrons in an atom. Okay. First quantum number, principal quantum number. Principal quantum number. Second, azimuthal quantum number. Azimuthal quantum number. Third, magnetic quantum number. Magnetic quantum number. Fourth, spin quantum number. These are four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. First quantum number is principal quantum number. Principal quantum number. It is denoted by the letter n. It gives the idea of main shells or orbits. Main shells or orbits. It also gives the idea of size of atom. Size of atom. Or it gives the idea of distance from the nucleus to outer shell of an atom. Size of atom. Okay. Its values are 1, 2, 3, 4, etc. 1 for K shell, 2 for L shell, 3 for M shell, and 4 for N shell. These are principal quantum number. Principal quantum number gives the idea of main shells. It also gives the idea of size of the atom. It also gives the idea of distance from nucleus to outer shell. Its values are 1, 2, 3, 4, etc. for K, L, M and N shells respectively. Then second quantum number is azimuthal quantum number. It is denoted by the letter L. It is otherwise called subsidiary quantum number or angular momentum quantum number. Subsidiary quantum number or angular momentum quantum number. It gives the idea of subshells. It gives the idea of subshells. Okay. It also gives the idea of angular momentum. It also gives the idea of angular momentum. Its values depends on the value of principal quantum number. Depends on the value of principal quantum number n. Its values ranging from 0 to n minus 1. Values ranging from 0 to n minus 1. That is, if n equal to 1, principal quantum number have the value 1, then azimuthal quantum number value have 0 to, instead of this n we have to write this 1, 0 to 1 minus 1, that is 0. If n equal to 2, L equal to 0 to 2 minus 1, that is 0 to 1, 0 and 1. If n equal to 3, then L equal to 0 to 3 minus 1, 3 minus 1, 2, that is 0, 1, 2. If n equal to 4, then L equal to 0, 1, 2 and 3. That is 0 to this 4 minus 1, 4 minus 1, 3, 0 to 3, 0, 1, 2 and 3. These are the values of azimuthal quantum number. Then third quantum number, magnetic quantum number. Magnetic quantum number. Magnetic quantum number, which is denoted by the letter M. It gives the idea of orientation of orbitals. Magnetic quantum number gives the idea of orientation of orbitals. Its values depends on the value of azimuthal quantum number L. Values ranging from minus L through 0 to plus L. If L equal to 0, then M equal to minus 0 through 0 plus 0, that is 0. If L equal to 1, M equal to, instead of this L, minus 1, 0 plus 1. If L equal to 2, then M equal to minus 2 through 0 plus 2, that is minus 2, minus 1, 0 plus 1 plus 2. Then if L equal to 3, M equal to minus 3 through 0 to plus 3, minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. These are the values of magnetic quantum number. Then fourth quantum number is spin quantum number. Spin quantum number denoted by the letter S. It gives the idea of spin orientation of electrons. Spin orientation of electrons. Electrons have two types of spin. Two types of spin. Two types of spin. They are clockwise spin and anti-clockwise spin. Clockwise spin and anti-clockwise spin. Okay, clockwise spin is represented by plus 1 by 2 and anti-clockwise spin is represented by minus 1 by 2. These are all about quantum numbers. Then some questions related to quantum number. Find n and L values of അല്ലെങ്കിൽ find the value of n and L of 3s orbital. 3s, n equal to this 3, value of principal quantum number, the given 3. For finding out the value of azimuthal quantum number, we have to draw 8 columns like this. Okay, 0, 1, 2, 3. S, P, D, F. Here S subshell value 0. Okay. Then next question. 4D orbital. 4D orbital. N equal to this 4. L equal to, here D orbital. D orbital. The value is 2. Azimuthal quantum number value is 2. Next question. Identify the orbital. Identify the orbital if value of principal quantum number is 5 and value of azimuthal quantum number is 3. This 5, write 5. Then L value, draw 8 columns like this. Okay, 0, 1, 2, 3. S, P, D, F. Here L equal to 3. 3. The orbital is F. So the orbital is this 5, 3. That is F. 5F subshell or 5F orbital. Okay. Next question. Find the value of all quantum numbers of the last electron of sodium. Last electron of sodium. Last electron of sodium. Find out the quantum numbers of last electron of sodium. Sodium 11. 1 S2, 2 S2, 2 P6, 3 S1. This is the last electron. Principal quantum number value n equal to this 3. Azimuthal quantum number value L equal to here S subshell that is 0. Magnetic quantum number, if L equal to 0, M is also equal to 0. Minus 0 through 0 plus 0, that is 0. Then one electron is present in that last orbital. So spin quantum number value is plus 1 by 2. These are the values of all quantum numbers of last electrons of sodium. Okay. Next question, of Bohr principle. Of Bohr principle. Electrons entering in orbitals in the increasing order of energy. Electrons entering in orbitals in the increasing order of energy. Electrons entering in various orbitals in the increasing order of their energy. That is, the order is 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc. At first, electrons filled in 1s orbital, then 2s, then 2p, then 3s, then 3p, then 4s, 3d, etc. Just like this. Electrons are entering in various orbitals in the increasing order of their energy. Next question. Pauli's exclusion principle. Pauli's exclusion principle. Pauli's exclusion principle. The principle states that no two electrons in an atom. No two electrons in an atom. Electrons in an atom can have same value for same value for all quantum numbers. Okay, no two electrons in an atom can have same value for all quantum numbers. All quantum numbers of two electrons in an atom is not always equal. Okay, generally electrons differ in their spin quantum number. One electron plus half spin, then another electron minus half spin. Okay, this spin quantum number difference. Electrons show the difference in their spin quantum number. Okay, no two electrons in an atom can have same value for all the quantum numbers or all the four quantum numbers. It is Pauli's exclusion principle. Next question. Hund's rule for maximum multiplicity. Hund's rule. Consider degenerate orbitals, that is orbitals having equal energy. Orbitals having equal energy are called degenerate orbitals. I have 3 degenerate orbitals, that is p orbitals. Then filling of electrons in this degenerate orbitals taking place just like this. At first, this one electron go to this orbital, this orbital, this orbital. Then another electron go to, or pairing takes place. Okay. So no pairing of electrons in degenerate orbitals. No pairing of electrons. No pairing of electrons in degenerate orbitals. Degenerate orbitals until all available orbitals possess one electron each. Okay, this is Hund's rule for maximum multiplicity. No pairing of electrons in degenerate orbital takes place until all these orbitals, available degenerate orbitals, possess or enter one electron each. This is Hund's rule for maximum multiplicity. Then electronic configuration of chromium, that is 24 atomic number, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Here exceptional configuration, 4s1, 3d5. This is half filled configuration. It is highly stable, so chromium show this configuration. Instead of this, we have to write argon. Argon 18 electrons. From here to here 18 electrons. 18 electrons. Remaining portion 4s1, 3d5. This is also the electronic configuration of chromium atom. Okay. Then electronic configuration of copper. Atomic number 29. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Here completely filled. D orbital is completely filled. So this copper show exceptional configuration just like this 4s1, 3d10. Here completely filled configuration of copper is highly stable. Instead of 1s2, 2, 3p6, we have to write here also argon 18 electrons, 2, 4, 10, 12, 18. 18 electrons. Remaining portion 4s1, 3d10. This is the exceptional configurations of chromium and copper. This chromium and copper show exceptional configuration, just like chromium 4s1, 3d5 and copper 4s1, 3d10. That's all about the focus area of first year chemistry, second chapter, structure of atom.